So I think everyone knows what's going on. Keep microphones muted during the presentations. And then at the end, when it's time for questions, so there'll be the 5 minutes for sort of question time between the talks, then if you can raise hands, yes, hopefully you all know now how to do that. Depends on what version of Zoom you have, but you can raise your hand either in the participants list, there's the icon, or you get yeah, I'm not quite sure why there's so many different versions of Zoom. I think they do this just to confuse us. So find whatever it is, there's an icon somewhere. So raise hand, and then I can ask you. But if you have problems with microphone, which I had yesterday when I tried to ask a question, for example, either we'll come back to you, or you can put it in the chat, and we'll sort of work it out from there. And after the session, there's a chance to meet the speakers. There are links on the website for the meeting as to where to find those rooms. Okay, so it is now sort of 10 o'clock, so I'm sure a few people will still arrive, but our first speaker is Jimena Gorfingel from the Open University in the UK, and she's going to tell us about Armatrix approaches to molecular photoionization. Okay, so thank you, Jimena.
Okay. Thank you, Graham. I'm going to start sharing my screen, and okay, I think, does that, marvelous, there you go, that should be. Yep. Okay, so yes, I'm going to talk about Armatrix approaches to molecular photoionization.
Do you want to make it full
and
screen?
Before
Jimena, do you want to make it full screen?
It is full screen. You're not seeing it full screen?
Well, we've got the sort of the next slide and the sort of screen.
Brilliant. It's not how it's supposed to be. I thought it was okay before. Yes, it wasn't.
It's fine. We can see your slides.
No, I know. I think I know how to solve the problem. Just bear with me because I had the problem before. You're gonna have to have. Sorry, you're gonna have. I'm sorry about this. We tried it before and I thought it was fine. Mm-hmm. I am going to do this, and how about now?
It's not coming up quite yet.
Okay, bear with me a second. And how about now?
Haven't got your screen yet.
Okay. Sorry, people. Let's try
that's
third time, and hopefully third time lucky.
That's the one. Yes.
Excellent. Okay, so I'm going to talk about Armatrix approaches to molecular photoionization. And before I tell you a little bit about the work we do and the methods and the software that we use, what I want to do is acknowledge the people that have been involved in the work. So the development of the software and performance of the calculations, it's a project that included a number of people, and particularly over the last few years, we had a collaboration with people at Queen's University Belfast, Hugo van der Hart, Greg Armstrong, Andrew Brown, and others, where we did a lot of the development of the codes. We also have, however, people beyond the UK that are involved in the code development, Karel Hufek in Prague and Alex Harvey in Berlin, who did some work some years ago. And fundamentally, a lot of the codes, or part of the codes that I'm going to talk about, time-independent codes, a lot of the recent development was done by Zdeněk Mašín, who was working with me at the Open University and then moved to Prague, where he has his own group, and Jakub Benda, who was a postdoc with me and now is a postdoc in Zdeněk's group in Prague. And of course, we have funding from a number of sources. So why the Armatrix method? Well, the Armatrix method enables basically the separation of the two difficult parts of the problem, if you want. On the one hand, you can describe the short-range effects, the exchange, the correlation effects, and on the other hand, the continuum. And that makes it very appropriate for all of the atomic and molecular processes that involve, say, a particle in the continuum. So for the description of the exchange and correlation, you can use well-established computational chemistry techniques, which makes it easy. You use tools that people have developed already, methodology that people have developed already. And the Armatrix approaches, although they come from nuclear physics, they have been used in atomic and molecular physics for 50 years or more. And the advantage there is that there's been computational implementations generally available since the 80s. And when I say generally available, what I mean is software that was developed by a group of people and was shared relatively freely by a number of researchers, those involved in the development and those who were not. And what does that enable was the creation of a group both of developers and users. And over the years, the number of developers have increased and decreased depending on funding and situations and so on. But it has meant that there has always been a certain group of people with expertise in the codes. And having a community of users brings two things. One, the fact that people test the codes, and whenever there are problems, bugs, etc., these tend to be reported. And on the other hand, the fact that if you have a number of people using the codes, it's worth putting the effort into the development, or at least it feels that several people are going to reap the rewards of the development that you're doing. Now, the fact that codes based on our matrix methods have existed for several decades doesn't mean that those, of course, are the codes that we use nowadays, yes? Because there's newer challenges, newer processes that people want to study, newer experiments that we want to compare with, and also because, of course, over the years, the computational power has increased significantly, we have had to rewrite the suites. And the project that I was talking about before, UK RAMP, for example, did a lot of rewriting of several of the codes. So let me tell you a little bit more about these Armatrix-based suites, and what we now have in the UK, collaborate outside as well, is what is called a high-end computing consortium on atomic codes. It's called UK AMOR. And basically what we do there is try to coordinate the development of the several UK-based Armatrix suites. So these are time-independent and time-dependent codes. They're interconnected. And the main ones, or the ones, they're basically suites. They're not individual codes, they're suites, and they're listed here. So we have the UK AMOR Plus code that I will talk about. This is a time-independent molecular suite. There is the equivalent for atoms or ionic atoms, which is time-independent, the time-independent atomic suite, and that's mainly these days maintained and developed by Conor Balance at Queen's University Belfast. Then there are the time-dependence codes, the RMT, the matrix with time, that is mainly developed by Andrew Brown and Hugo van der Hart and Queen's University Belfast. And this is partly based on earlier codes that were developed there by Ken Taylor and his collaborators. We have a library, GBTO-Live, to calculate molecular integrals, and this is an independent library. We'll talk about it more later. And what we also have that is now in development is an Armatrix-based heavy particle collision code as well. And as you will see later, some of these are interconnected. So what's the basic idea of the Armatrix method? As I said before, there's a separation of the problems, of the two parts of the problem, and this is based on the separation of space. When you have your free electron being a photoionized electron, or an electron, for example, in an electron scattering process, because the UK AMOR Plus code started codes to describe electron and positron scattering from molecules. So when this electron is close enough to your molecule, to your target, exchange and correlation are important. So if you want to describe the system, the n+1 electron system accurately, you need to do it. It's explicitly multi-electronic. You need a multicentric expansion, and we use basically quantum chemistry techniques. However, after a certain distance, from beyond a certain distance from the center of mass of the molecule that we define by an Armatrix radius, the electron becomes distinguishable, and therefore exchange is negligible, and correlation becomes something very simple. You basically can describe it as a polarization of your target or residual ion by your free electron. So in that case, you can treat explicitly only one electron, and the interaction between this electron and the molecular target can be simplified and described as a long-range multipolar interaction. We work all the time in these methods with molecules within the fixed nuclei approximation. So the nuclear motion is not coupled. So as I mentioned before, we have time-independent and time-dependent codes, and we can perform ionization calculations with both sets of codes. So to do time-independent calculations, we use the UK AMOR Plus suite only, and these calculations are less demanding than the time-dependent ones, obviously. And what we can calculate is single photoionization observables, so angle resolved and final state resolved cross-sections, symmetry parameters, photoelectron angular distributions, Dyson orbitals, etc. There is in the code of functionality, and to hear about that, you're going to have to wait for a couple of talks because Jakub Ben is going to talk about it later this morning. Now, when it comes to the time-dependent calculations, you need to use both the RMT code that I mentioned before and the UKRMO Plus code. And the implementation of the treatment of molecules in the RMT code is recent. So far, we've only studied small molecules in linearly polarized fields, relatively simple processes, but the potential to treat processes beyond the perturbative regime is huge. There's a lot of work that has been done on atoms, for example, for arbitrary polarization, harmonic generation, etc. And you've got an example there on the slides on the right of what is 3-photon ionization of potassium. So that is a comparison between experimental and theoretical momentum distribution for counter-rotating circularly polarized pulses. So it's work of, again, Queen's University Belfast with Jakub and other collaborators. So let me tell you a little bit about the theory of both types of calculations, and then hopefully I will show you some results. So as we've heard so far, the main quantity to calculate here is the molecular frame partial wave dipoles, and and these can be calculated, calculating the transition moments between an initial bound state and a set of final bound and continuum states of the neutral target of the n+1 system. So in our case, we expand those functions in terms of what we call our matrix functions, so the linear combinations of these our matrix functions, and that's what I've done. I've included that here. So what we see is that we have to calculate the transition moments between an initial bound state and all of these bound and continuum states. So from these quantities, we can calculate cross-sections, we can calculate symmetry parameters, and if we want to calculate photoelectron angular distributions, those again can be calculated in terms of the molecular frame partial wave dipoles using Wigner matrices, transformation, etc. So a lot of the physics comes from describing well these R matrix basis functions. And these are calculated in the inner region of these R matrix problem. And to generate these, you need three components. You need to describe the residual cationic states of the system. And for these, we tend to use CAS-SEF methods. So we will describe the wave function in terms of a configuration interaction where the orbitals can be optimized at the CAS-SEF level. Now, this is a closed coupling expansion of the type that you saw, for example, in the XChem presentation yesterday. And the second set of terms is what we call L-square functions, and these describe correlation polarization. And for these are expanded in terms of the orbitals that we have used before for the description of the cationic states. So we have some rules for which kind of configurations need to go into these L-square functions, depending on how we have generated these cationic states and how much of the polarization we need to describe, etc. The next ingredient is the description of the continuum, of the electron in the continuum. And for that, we use something that we call continuum orbitals. There are one particle orbitals, and these are expanded in a combination or independently B-splines and Gaussian type orbitals. So this again may remind you of the XChem talk yesterday, and what we do is something similar, but we have more functionality in our course. And this is where this GBTO lib that I mentioned before comes into play, because we decided that we wanted to develop this as a separate entity, and all of the integral calculations, something that is object-oriented, is a parallel library, and that it was designed in this way so that it could not only just be used with the UKRMO Plus codes, but it could be used by other developers who wanted to use it. So for example, we had a couple of years ago a project with Vitali Aberbuk and Marco Ruberti at Imperial College, where we interfaced the GBTO lib library with their B-splines ADC code. So this GBTO library will do all of the integral and orbital operations that you need for this kind of calculation. So it will calculate the 1 and 2 particle integrals between Gaussians and B-splines. It will transform them from the basis of atomic functions onto molecular orbitals. It will perform orthogonalization of the orbitals, etc., etc. And what our library allows us to do is two things. We can describe the continuum using a mix of Gaussians and B-splines. So if you look at the picture below here, what you can see is that, for example, we use Gaussians for the molecular orbitals. That's always the case, because then we can use the expertise of quantum chemistry. So we will have a Gaussian here. And to describe, for example, and to describe the continuum, what we do is we put Gaussians on the center of mass of the molecule. These are diffuse Gaussians that will describe the continuum up to a certain radius given by this. And from that onwards, we use B-splines. Now, we wanted to be able to do calculations without having to use Gaussians for the continuum, and that is also possible with a code. So the example, the case, it's shown by this figure where we have the same Gaussian on the atoms, but in this case, the whole of the radial part of the continuum orbital is described by B-splines over the whole range. Now, why did we want to do that? There's two reasons. First is, why not? For small systems, you pay, of course, a computational cost if you're only using B-splines, but it's feasible. And the examples I will show you, many of them use B-splines only continuum basis. But on the other hand, from the experience of using Gaussians in electron scattering, we know that sometimes Gaussians are not very good when this radius has to be quite large. If you're using Gaussians here that are quite diffuse, and therefore you need to use your Gaussians to describe the continuum for quite a long range here, the quality of the description can be poor, and therefore we wanted to make sure that we could solve the problem by using B-splines for a radius closer to the bound Gaussians. So to perform calculations, you can see here on the left, basically a flow chart of what programs we use. This looks very complicated. It is a little bit, but nowadays we don't have to do this manually. Carl Hufex some years ago got fed up with having to do this manually because he was doing calculations for hundreds of geometries, not for photoionization. He was doing associative detachment studies, I think. And therefore he wrote some set of Perl scripts that have been modified since, that have made calculations much easier. So the other thing I wanted to highlight from this is that we do not perform the calculations of the orbitals, be them Hartree-Fock if we want to do simple calculations, or CAS-SCF orbitals within the codes. What we use is we read these from a file generated by external codes. So this file is in Molden format. So Molden format is very general and can be in principle generated by any quantum chemistry code. We systematically use MOPR as a code that you have to pay for, but it's reasonably cheap. You can also use Sci4, that is freeware. It hasn't got all the functionality of, say, MOPR or presumably MOLCAS, but you can use it as well. The suite is a Fortran 95 codes with some 2003 functionalities, and it needs standard libraries to compile, and optionally some others. So for example, the Hamiltonian build that is done by this code is called SCAT-CI, or its parallel implementation MPI SCAT-CI. If you use SCAT-CI, you can either use CalAPAC to perform the Hamiltonian diagonalization, which can be for big problems, the bottleneck of the calculation, or if you really have a huge Hamiltonian, you may be able to use SLEPC for the calculation. So the last thing I wanted to point out is this SCAT-CI integrals program is basically a relatively simple program that uses this GBTO live that I have mentioned before. So what about the time-dependent calculations? Okay, in this case, we use RMT, and what you do is you solve the time-dependent Schrodinger equation. So in the inner region, this is the equation that you solve, and of course, your Hamiltonian is the sum of a term that is field free, of course, and then a term that includes the interaction with the field. Our now time-dependent wave functions are solved again as an expansion on the R matrix basis functions, and these are generated by the UKRMO plus code. So you can see here that for time-dependent calculations, we need both codes. For the atomic case, they use another code. If they want to do RMT calculations for the molecular case, you use UKRMO plus. So to solve this problem, we have a set of differential equations that can be written in matrix form. The Hamiltonian elements indeed are linked to the transition dipoles. And note here that whereas before the transition dipoles that we were looking at were those between the initial state of our molecule and all of the R matrix basis function, in this case, what you have to get is the transition dipoles between all of these R matrix basis functions. So the data that you need is significantly larger from the time-independent codes. As I am talking, I realized that in different slides, I jumped from having the m+1 superscript here or not, but these are always the R matrix basis functions. Okay, so the S matrix has some surface terms, and the surface terms are basically calculated as a product of the derivative of the outer region radial wave function and something that is called the boundary amplitudes. So the boundary amplitudes are basically the projection of these R matrix basis functions on some wave functions that describe the state of the residual ion and the angular behavior of the free electron. This is what we call the channel functions in a way. And to perform this differentiation, what we actually need to do is we do it numerically. So in the case of time-dependent calculations, when we set the boundary, the radius that separates the inner and the outer region, we actually need to put it a bit further away than we would do it for time-independent calculations. And the reason for that is because we need a range, a set of bond lengths in which we calculate this numerically and the amplitudes numerically that is inside, say, that Armatrix radius. So within the inner region, this is what we do. When you go to the outer region, the problem is simpler, of course, and the wave functions can be expressed as a product of the residual ion and electron-angular behavior wave functions, they are the channel functions, and these reduced radial wave functions that I mentioned before. And these come from solving a simple set of differential equations where you have a one electron Hamiltonian and an interaction potential that contains the long-range coupling between channels, the laser interaction with the residual ion, and the laser interaction with the ionized electrons. So this is solved with a finite difference discretization. And what is important here is that the grid in which this is solved needs to be large to prevent reflections of the ionized wave function from the end point. So when you use UKR+ to generate the inputs for the RMT, you use most of the programs that are the same, but as I mentioned before, the data requires significantly more. Specifically because, as I mentioned, you need all of the pairs of transition dipoles, but also because, as I say, you need larger matrix radii, because you need this grid overlap. In the RMT calculations, the time evolution is done by an Arnold method. And something that we found with the tests and some of the calculations that I'm going to show you soon is that the quality of the time-independent results that we get using the same, say, quantum chemistry model gives an upper limit to the quality of the time-dependent results. So getting the UKR+ input right, the data right, is quite important. So this software, I mentioned before, the UKR+ codes tend to be freely available, and we release the software, both the UKR+ suite and the RMT. So the RMT code can be downloaded from GitLab, and the UKR+ suite we make available on Zenodo. So Zenodo is a website for you, those of you who don't know it, where you can deposit data, codes, etc. And the advantage there is that you can publish different versions. So whenever we find a bug in the code, so we implement new functionality, we release new versions, and every new version has a DOI associated to it, like a paper. And what that means is that whenever people use the code, they can very clearly cite it by using the DOI and be specific about the versions of the code that they can use. So if you go to Zenodo and try and type UKR+, you will find the UKR+ suite, the inner and the outer regions. The codes are published separately, released separately, and the GTO bus library. The codes include CMake-FAS and a test suite, so I would say they're reasonably easy to install and run. Maybe not, depending how much experience you have. But I wanted to mention something else that we're doing at the moment, and there is a US-led initiative to make atomic and molecular physics codes readily available to use by the partners with this initiative and also by the atomic and molecular physics community at large. So this is in a very early stages, but it's what it's called a gateway. And the idea with that is that there is a web interface where you can log in, and there's a simplified way of producing input for the codes and a simplified way of extracting output. So at the moment, there are a number of codes that you can see there on the right, and you will see some usual suspects. XChem is there, Armin's Quincy's codes are there, ePol Bob Lucchese's code is there, some electron and positron scattering codes are there too. And this is linked with some supercomputers in the United States, but there's no reason why it couldn't be linked to other computers or gateway cloned and linked to other computers. So this is in the very early stages, but we hope to make developments here and make sure that the codes that are being developed by the community can be used more widely. So let me now try and move to some examples of calculations that we have done, and I will present both time-independent and time-dependent results. So this first result is one photon ionization of H2, and this is the symmetry parameter. And what I wanted to show here is that when we perform the calculation for a single geometry, so for the equilibrium geometry of H2, we get an asymmetry parameter and the curve you need to look at here is the gray curve, where you can see peaks that are associated to the resonances that are present in the system. Of course, in general, the experiments do not have the resolution to describe those resonances. So if what we do is a vibrational average of the symmetry parameters, what we get is this reddish brown curve where the resonances are no longer visible, and the agreement with the most recent experiments is on the whole very, very good. So in the same way that we do one-photon ionization calculations with the time-independent code, we can do two-photon ionization with both the time-independent and the time-dependent codes. So here I'm showing you the two-photon ionization of H2. And what we were doing here is trying to understand how, what we needed to perform accurate calculations with the RMT codes. So what you see in the first picture here is a comparison of several types of calculations. So to generate the UKRMO plus input, we use a B-spline only continuum. We try two types of basis sets for the bound molecular orbitals, augmented basis sets, a double zeta and a triple zeta. The calculation is equivalent to what would be a full CI. And these results that I'm showing you are for parallel polarization of the field, parallel to the molecular axis. So in this first figure, what you see is calculations. The full lines are UKRMO plus time-independent calculations. And the red one is with the double zeta basis and the blue one with the triple zeta basis. And you can see that the agreement is very good between the both of them for lower energies. But when you go to higher energies, the results start to differ, particularly in the proximity of this second resonance. Now, the RMT calculations with exactly the same input are plotted with empty and full dots. And you will see that the results are very close to the time-independent ones, but they are not exactly on the curve. You can also see as dashed lines some results from Morales et al., which I think are from Fernando Martin's group and the DFT-based calculations. So the agreement of all of them is very good, but something that you would notice is the differences are largest where the resonance is. But the other point is that we realized that in this case, when you use the RMT code to achieve good agreement with the time-independent results, you need very long pulse pulse turn. So the blue dots for the triple zeta bases, the empty ones are for a turn-on of 30 cycles, and the full dots are for a turn-on of 300 cycles. And you can see here, for example, how that point comes down here to basically full agreement with the time-independent codes. And you can see that there are differences even at lower, smaller, but differences at lower energies here too. So that's something that we learned, that we needed that in the time-dependent codes. The other thing that we noticed or discovered is that for the time-independent calculations, we needed to make sure that the size of the R matrix box is important. We needed to make sure that the R matrix boxes were large enough. So the comparison is here with earlier calculations, and you can see the blue curve results with an R matrix box of 30 Bohr, and the green one is with 50 Bohr. And you can see how when we increase the radius to 50 Bohr, the agreement with the earlier results is actually excellent. So some more results. These are not calculations that I've been involved with. These are calculations from Olga Smirnova's group, and these are photoelectron angular distributions for NO2. So this work was done, I think, because then they went on to study the dynamics, at the conical intersection, the photoelectron spectroscopy, the dynamics of the conical intersection, and I'm sorry I haven't got the reference there. So they were interested in studying the photoionization for a number of geometries, and here you see results for 3 different angles between the NO bond length. And you can see the photoelectron angular distributions here. This is a calculation that was done not with B-splines, but using Gaussians only for the continuum, because in 2017 we did not have the B-spline implementation in a shape that it could be used for these kind of calculations. Now, what the GBT library allows you to do is to compile and run the codes in quadruple precision. So the problem with using Gaussians for the description of the continuum is one of linear dependence. We work with fully orthogonal orbitals, and if you have to use a lot of Gaussians, you start to run into problems of linear dependence. Those problems can be ameliorated, and in the cases that we've tried almost solve completely, if you move from running the codes in double precision to particle precision. And that's something that this GBT-only library allows you to do. We have done also, the codes had also been applied to bigger systems, to substituted benzene molecules, for example, but using simple models. So let me show you another example for ionization of water. And again, this is another case where we have used the B-spline only continuum. We can do it for these 3 atom systems. And what you have here on the left is cross sections, and on the right are symmetry parameters for ionization into specific states of the cation. So the ground state, the first excited state, and the second excited state. So in the case of the cross sections, the results are presenting as smooth. So we convolute the results to get rid of the very fine resonances that are not detected by the experiment, or that in some cases would not be there because of the vibrational motion. And you can see that the agreement with prior experiments, and prior calculations is very good. And on the right, you have the symmetry parameters. And here we've plotted both the raw results from the Yokoyama Plus code. So that's the gray curve where you can see all of the spikes given by the resonances. And then these convoluted smooth results, which are again the red, brown full curve. And again, agreement is very good here. And I wouldn't like to say whether it is any of the theoretical methods that actually provides a better description. The spread of experimental results, I think, doesn't allow us to say. So let me move now beyond what we can do perturbatively and move to strong field ionization of water. So here, what we wanted to do was to see if we could reproduce results from an earlier calculation, a single active electron calculation, and therefore we went for simpler models. So there are 2 types of models that we use. One is a single channel, where we basically run a separate calculation for each of these 3 lowest states of the cation of H2O+. You see the results on this column. And then a couple model where all these 3 channels are coupled. So on the left, you see the orbitals for which the electrons are ionized for each of the states. And here, what you see are the projections of the ionization yields on the X, Y, Y, Z, and XZ planes for these 3 states in the 2 models. This, again, was a B-spline only calculation, but here the wave functions were not described as the CAS-SCF level. They were described as at the Hartree-Fock level. So what we did is many calculations for linearly polarized light from many orientations, and I have no idea why that went back on its own, and with an intensity of 20 terawatts. So what you can see here is that when we do the single channel calculation, the ionization yields have basically similar shapes to those of the orbitals from which the electron is ionized. And therefore, what I'm trying to say is that the maximum of the ionization yield is consistent with the maximum of the electronic density of the orbital. However, when we couple the channels, what we see is that the ionization yields, all of them have basically the shape of that of the X state, okay? So what is happening here is that the state coupling, both field and correlation related, basically redistributes the ionization yield of the lowest of the X state. The only exception is that in the case of the A state, some of the distribution that came from the shape of the A state is retained, as you can see here on the projection on the Y-Z plane. The other thing to notice is how the intensity, how the size of the yields changes. So whereas the yields in the single channel case go from things that are of the order of 10 to the -6 to 10 to the -7 and 10 to the -10, the changes in the couple model are from 10 to the -6 to 10 to the -7 and then 10 to the -8. So to show you these results better, there is a comparison here. Now, basically, these pictures are plotted, is the same plotted on the plane. And now we are comparing with a single active electron model. And in looking at the paper, we realized that in the paper that was published is a Fils-Réveil paper. You had the reference in the previous slide. Fils-Réveil made a mistake, and instead of having dashed curves for the single channel model and full lines for the coupled channel. The figure at the moment has full lines for all of the channels, so you cannot tell the difference. So I got in touch with FISREVE a day or two ago to ask them to correct the picture. So again, what you can see here is that when you looked at the dashed lines, and this dashed line here cannot be seen because it basically goes right under the SAE model. For the dashed lines, when you look at the same plane, the distributions are different. You know, the maxima are of different along different axes, so along X here and along Z here. But when you couple the channels, you can see that the distributions go more or less along the same axis. You can see it here, and you can also see it here with the green curve. So I think I've got to the end of my talk, and I hope I managed to show you that the Armatrix approach, both in the time-independent, time-dependent versions, allows us to provide accurate descriptions of photoionization. We've spent the last few years doing a lot of software development, and what we hope to do now is to do applications of it and exploit it to study interesting physics. And when I say we, I just don't mean myself. I mean, as you will hear later on, Jakub Benders, the ENIC machine, our colleagues in Belfast, etc. So for the time-dependent calculations, I think we will have to stick to smallish molecules. The time-dependent calculations, the empty calculations are quite demanding, and I think we're not perhaps yet at the stage where we can really treat, for example, biomolecules. We might need some further software development optimization to do this. And for the time-independent calculations, however, we think we can do bigger molecules and we can do some other things, and you will see Jakub's talk later today. And before I stop, I just wanted to remind people of something that's not related to my talk, or yes, in some way. Many of you would have got an email from Fernando some months ago saying that the COST Action is planning a special issue in computer physics communication on attosecond chemistry and physics software. So the guest editors are myself, Luca Genti from Florida, and Fernando Martin. And if you're interested, you may have got in touch with us already to let us know that you're interested, but if you're not, please do. And the idea is these are papers that describe software, so you need to have the paper and the software ready. And we plan for the deadline, submission deadline for this special issue to be around the autumn of next year. And thank you for your attention.
Thank you, Jimena. Okay, so are there any questions? While I'm waiting for people to sort of think of questions, Jimena, why exactly, can you just tell me briefly, so what actually is really the difference, the key difference between the Armatrix method and the sort of B-spline method that Fernando and Vincent and so on do? Because I thought that you divided the problem to the two parts, but your basis functions, especially with the B-spline continuum, seem to do much the same now because they're covering the whole space.
Yes, they do, because you have, you have to, in a way, cover the whole space. The main difference is that we use this trick of the Armatrix, which is that we solve the problem in the inner region, then we build what is really called, I may even have a slide here, but what it is an Armatrix, okay, which is something that allows us to, if you want, to match the inner region and the outer region solutions, okay? Mm-hmm. Or if you want in another way, we use the inner region, the inner region results to solve the differential equations in the outer region. So that is the difference, that we use this Armatrix that is built, from the boundary amplitudes and the Armatrix functions, and they don't.
Okay. So it's just really the analysis of the problem that you're just using that part on the way in which you solve the problem. Yes, in a way in which you use the parts that you put into to solve the problem. Yeah. Okay. Thank you. That makes sense. So we have questions. So Fernando.
Yeah. Well, thank you very much, Jimena, for this very nice talk, very complete. I have a question, a curiosity. Could you tell us an estimate of what is the difference in computer time between the two approaches you mentioned, that in which you only use B-splines to describe the continuum, and you use B-splines and monocentric Gaussians, not for a diatomic, let's say for a regular molecule of, I don't know, a few atoms, 5, 6. You have the, just to grasp if how much additional computational effort is needed.
Okay, so
we do all B-spline calculation.
For a big polyatomic molecule, say pyrazine, for example, the example that Vincent was showing yesterday, we haven't done B-splines only. I think that would be too computationally demanding. That would be unwise at the moment, okay? But for a triatomic molecule, the difference, it depends on what basis you use to describe your bound orbitals, okay? But the difference could be hours. I'm not going to, lie about this. The Gaussians, the integrals, most of them are done analytically. So, you get high accuracy with little effort. With the B-splines, the integrals are done numerically. So to get the accuracy, you need to put the time in. But in terms of, for example, if you're using RMT, if you're going to do RMT calculations where that part of the problem is going to take hours anyway, the additional cost, is not a large percentage of the time that the whole calculation is going to take. And this is where we think, well, if we're going to spend a few hours calculating the integrals, well, we're going to spend a few days perhaps doing all of the RMT calculations. So what does it matter, really? So that's the thing. But yes, the difference is significant. Yeah.
Okay, thank you.
And there's a question from Jesus.
Sorry, just a curiosity. When you use the TGT of Leaf, that is very, very nice. How is the behavior with the contractions? No, because in general, there are like two methods to do the integrals. Ones are like more based in non-contracted integrals, and the other ones, like for example, Molcas in the C1 and also Molpro now, they have more contracted base integrals. And the GT of Leaf is going to be more like more contracted or less contracted, let's say.
I'm not sure I understand your question, Jesus. Sorry.
So there are like two types of algorithms to do these integrals. No, one is first I do the contractions.
You mean the contractions of the Gaussians?
Yes, the contractions of the Gaussians, because this can be very expensive depending on the basis. So do you have it optimized for contracted basis or not?
I will confess, I don't know. I would have to go and have a look. Come and find me at the Meet the Speaker. Okay. Zdeněk will probably be there as well, who knows all of the details of the code, and we'll discuss this. Okay.
Okay. Thank you.
You're welcome.
So just a quick question before we move on, and this is from Zdeněk.
Sorry, well, I was just raising my hand perhaps to just answer Jesus, but we can leave it for later.
Is it a quick answer?
Yes, we do optimize for contractions, and I can provide some details. Okay.
Perfect. Thank you.
Thank you. You may also meet later and discuss more in detail, I'm sure, the three of you. Okay. So thank you, Jimena. And we shall now move on. So our next speaker is Alex Kulev.
Yeah. Let me share my screen.
So Alex Kulev from Heidelberg, and he's going to be telling us about ultrafast non-adiabatic dynamics in molecules following ionization.
Wait, this was okay. See the presentation and not the next slide.
I can see yes, exactly, and I can see your mouse and everything. So over to you, Alex.
Okay, let me just put probably a pointer just to see it better. Okay, of course, first thanks to the organizers for giving me the opportunity to present our work, and of course, many thanks for setting up such a wonderful program. There was very many exciting talks that I was able to listen to. What I would like to present is what we did, let's say, recently, and something which, of course, we do for already quite a while, is what is the dynamics in the molecule after we ionize it. So in order to study the dynamics in molecules, of course, what we have to do, let's start from the beginning, we have to solve the molecular time-dependent Schrodinger equation. This is, of course, what I will concentrate here is I will exclude the process of ionization. So something what Jimena talked before me. And this is, of course, as we saw and as we know, science by itself in a huge field. It's a very complicated problem. So this not only will complicate our task to describe the dynamics after the ionization, but it will also put us in a different, let's say, physical setting. We will not be so much interested in the way of producing the ionic states or the initial state of the system. We were more interested in how the system will evolve afterwards. So it's in a sense, it's not so important for us whether we do the ionization by a laser, by scattering an electrons, positrons, or whatever. We just want to populate certain number of electronic states, as we saw, so to create an electronic coherence and to see how the system will evolve in time afterwards. So in principle, the Hamiltonian that will sit here, I put just the molecular Hamiltonian, but of course this can include also an interaction with the field if we want to add a field and to study how the field then can modulate the system, or let's say doing a probe pulse and so on. So all the methods that I will present will be also applicable if we include a time-dependent part of this Hamiltonian. Now, the problem is that, of course, we cannot solve this equation. Yeah, as we all know, it's too complex if we go beyond 2 particles, so we cannot do this in its full complexity, and we usually need some sort of approximations. Now, the approximations that we somehow tend to always try to do is to keep, because of the huge success and of the Born-Oppenheimer approximation, we always tend to separate our problem into an electronic and a nuclear problem. So to separate our full molecular wave function, which depends on all coordinates of electrons and nuclei, into something which, let's say, we can try to do the electron dynamics in the fixed nuclei, which we did a lot in the past. Or we can, of course, do nuclear dynamics on potential energy surfaces. So the electronic states, the notion of electronic states, of course, also come from the Born-Oppenheimer approximation. So this is, let's say, in the framework within which we want to keep somehow and to analyze our results. So the main question is how we can merge those two, how we can, on one hand, have described well the electron dynamics and see what the electrons are doing, and on the other hand, have the description also on the nuclear dynamics, which we'll set in at some point, and of course, not losing this nice idea of separating the electrons and the nuclear. So before showing how we can do that, let me just discuss 2 important points in describing the dynamics in ions. One is the electron correlation. Yeah, even at fixed nuclei, this is extremely important, and this one can see if one tries to describe or to get the ionization channels or the ionic states, cationic states within an independent particle model. So being this Hartree-Fock or DFT or so on, the only way to describe the ionization states in a system is by applying somehow to remove electrons from particular orbitals. So what we will get when we do that is, of course, some states, which will be lines here. We have fixed nuclei, where each state corresponds to the system with 1 electron less in a particular orbital, where the different colors represent, of course, different orbitals. So this, in, let's say, second quantization language, this will be something we apply some annihilation operator on a single Slater determinant, yeah, of some orbitals. Now, of course, this is known already for a long time, that the situation is actually quite more complicated when we include the electron correlation. When we include the electron correlation, not only that these states will move and will shift because of accounting for the electron correlation, we'll have additional effects which we won't be able to describe within a single electron or independent particle model. So we'll have, due to the correlation, we can have, let's say, mixing of this one-hole correlation, so of one-hole configurations. So electrons missing in different orbitals can couple and form ionic states, or we can have things which are completely impossible to describe within one particle picture. These are like satellites states, or additional states which appear due to, let's say, excitations that we can trigger into our systems, like what is shown here, or a complete breakdown of the molecular orbital picture. This means that removing an electron from, let's say, an inner valence orbital, instead of populating a single ionic state, will actually populate a large multitude of ionic states. And we know that this implicitly means that we trigger electron dynamics, so populating many ionic states so we create an electronic wave packet. So including the electron correlation gives us first a way to construct or to create an electronic wave packet completely naturally, in contrast to the way we can construct electronic wave packets in the independent particle model approaches, where we implicitly has to or explicitly has to couple more than one orbital in our consideration. Here we can do exactly the same. We can, of course, couple many orbitals, or ionization from many orbitals, but the electronic correlation will give us something additional, which is we won't be able to describe within the independent particle model. So electronic correlation is important, and this is something that we need to keep to account. Now let's see what the non-adiabatic dynamics, or the dynamics, the moving of the nuclei can give us. Of course, as I said, Born-Oppenheimer is something which is the other, in a sense, important, or the milestone in quantum chemistry. The question is that the Born-Oppenheimer approximation is, of course, defined on a single potential energy surface. So we don't couple different potential energy surfaces. As we said, if we want to trigger electron dynamics, this means that we have to populate several electronic states. And if we populate these states which are not coupled among themselves, so we got something rather trivial as a nuclear dynamics. So the wave packets will run on these potential energy surfaces completely independently. So we need to include, of course, non-adiabatic effects. And there are two regimes. I will cover both of them. We'll give you examples from both of them. One is when we have in the outer valence, when we couple just a few states, we have less dense spectrum in the outer valence. So here, of course, the things are, of course, more involved than in the case of non-coupling states. So we can transfer, of course, already populations. So we have, in addition to the electron coherences that we create, we can also destroy these coherences by moving the nuclear wave packets on these potential curves, and also by transferring population from one state to another through non-adiabatic effects. Now, what I would like to cover also is something which we have in the inner valence regime, where we saw even removing an electron from a single orbital can populate a large amount of ionic states. So we get some sort of a salad like that, which is, of course, with many conical intersection in between, and it gives rise to a very complicated dynamics. But we will see that we also can attack, and how we can attack this problem. Okay, let me briefly present you the way we did this recently in a couple of examples. So, as I said, we want to stay within the idea of having electrons and nuclei somehow separated for interpretational also reasons. So what we start with is, in principle, exact bond one expansion. So we use our electronic states or cationic states as a basis, which they form a full basis. And we have these expansion coefficients in front, which are, of course, our nuclear wave packets, which run on these potential surfaces. So the time dependence is only in the nuclear wave packets. Now, of course, the electronic states are solutions of our electronic Schrodinger equation. And as I said, the better approximation we do here, including the electron correlations, the better, because we have a better description of this part. So in a sense, the first step in this scheme is to construct our potential energy surfaces. Unfortunately, of course, when we do this, we are implicitly within the adiabatic representation. So as we all know, when we do this, then the Schrodinger, the time-dependent Schrodinger equation for the nuclear wave packets starts to look a bit nasty. So we have a non-adiabatic couplings element coming from, of course, action of the nuclear kinetic energy on the electronic state. So we have our derivative couplings, which is quite difficult to compute. And what one usually needs is to go to do some sort of diabatization, to go to another representation in the electronic space, diabatize the electronic space such that we move, in a sense, the derivative couplings. So we move from a derivative couplings to potential couplings within the matrix W here. So the transfer of population is done not by gradients on the electronic surfaces, but by a simple potential matrix. Of course, the diabatization is also a huge field by itself. What we used, and in the examples that I will show, is the Vibronic coupling method, which works extremely well for, let's say, a situation when we don't have large amplitude motion. So when the system doesn't change much after the ionization. These will be the examples that I will discuss. So the Vibronic coupling Hamiltonian method was also developed long time ago, applied extremely successfully by many, many people, including, of course, our chairman today. So in a nutshell, this is a Taylor expansion of the potentials, and we include different terms in also coupling terms here. And the idea is that when we diagonalize our Vibronic coupling potential matrix, we have to recover the adiabatic potentials that we have constructed through some sort of electronic structure methods. So these parameters here in front of the different terms are something that we need to fit and to find the best fit of it. So the step number 2 in the process is to construct the Vibronic coupling Hamiltonian. And with the Vibronic coupling Hamiltonian, then we can propagate our initial state. So as I mentioned, the initial state here, because we want to have also electron dynamics, is different from what traditionally is done when one is using or one is interested only in the nuclear dynamics within excited systems, or in the photodynamics or the photochemistry, usually where a single vibrational wave packet is propagated on many electronic states. Here we have to start, so our initial state is a superposition of many electronic, states. So we have several or many vibrational wave packets which are running on these coupled multidimensional potential energy surfaces. So we have to propagate or to solve the time-dependent Schrodinger equation. And since, of course, we are in Heidelberg, what we use is the MCTDH. I won't present anything from the MCTDH. I expected that Fabian will do this on the first day, but it was mentioned already by Luik. So for those who are not familiar with the MCTDH, or who are not familiar, they have already some idea. It's a way of solving the multidimensional coupled problem, or propagating wave packets on coupled multidimensional surfaces. So let me discuss the last point in what we need to do in order to visualize at the end what we are doing, or to analyze our results. Traditionally, what we always did when we were doing electron dynamics on fixed nuclei was to use the density, electron density operator, or Hall density. In this case, it's time evolution. Here, the things are a bit more complicated. We need to integrate, of course, not only on the electronic degrees of freedom, but also on the nuclear degrees of freedom. So if we first integrate on the n-1 electron degrees of freedom, we will get our density matrix, which will depend also on the nuclear coordinate. The question is that within the adiabatic basis, so if we use the diabatic states, our density matrix will be very little, in principle, dependent on the nuclear positions, on the momentary nuclear positions. So within the diabatic basis, we can assume that the density doesn't change much with changing the nuclear position. So we can take this quantity out, and then what we will have at the end will be a density where all the time dependence actually will come from the overlap of the different vibrational wave packets running on the different coupled electronic potential energy surfaces. The computation of the electronic density can be done like always, like usual. Now, let me show you two examples. First is something that we did on propiolic acid, and when we studied the charge migration in propiolic acid. So this is the outer valence spectrum of the propiolic acid molecule computed by ADC and Green's function calculations at equilibrium distance. So what we see here is that we have this whole mixing that I was mentioning at the beginning between the HOMO and in principle the HOMO -2. The third and the fourth states are from different symmetries. So in principle, they can be addressed differently. So what happens if we, let's say, ionize the HOMO, which is more or less localized on this carbon triple bond, we will induce these pure electronic oscillations between the carbon triple bonds and the carbonyl oxygen here. So this is what you see here. So at fixed nuclei, this, of course, oscillation will last forever and will go back and forth between the two ends of the molecule. The question is how this changes and how this dephases when we include the nuclear dynamics. This was a large debate, or still a debate in the community, how fast this decoherence from the nuclear motion takes place. So if we want to do this, we took all the 15 normal modes, or the 15 nuclear degrees of freedom of the system. We constructed the Vibronic coupling Hamiltonian over all these modes. So this is just one shown here, just to see how the Vibronic coupling Hamiltonian works. So the dots are, of course, the adiabatic energies, and the full lines are coming from the diagonalization of our Vibronic coupling Hamiltonian. Then we have constructed the initial wave packet. So this is, as you see, we need to populate, in a sense, two states. They are populated such that they reflect the removal of the HOMO electron from the system. What is shown here is this whole mixing parameter. As you see, at different geometries, of course, these two orbitals mix differently, so this has to be taken into account. Of course, we have a large mixing, so like at position -2 in this mass-weighted coordinates, and the equilibrium, we have this, as you see, something like 70 to 30% mixing in the two. So this is in this particular mode. Of course, we have this in all modes. So we construct the initial state and we propagate it. So now what you see here is, as I mentioned, the overlap between the wave packets. So what are shown here are the important ones. Of course, up there is the population. So we don't have strong non-adiabatic couplings here between the states. So there's very little transfer population due to the non-adiabatic effects. But what is important here is how the coherence is kept. This is, in a sense, the off-diagonal elements in the overlap of the wave packets give the coherence between the two states. So we see that we keep the coherence for about 10-15 femtoseconds. This is the full, as I show you how the density or the whole density of the system. We start with something which is localized on the triple bond, and this is the way how it dephases. It makes a few oscillations before it gets dephased and distributed along the molecule. Now, this is something that we did recently. I wanted to show you also the theory behind, but if you are interested, you can look in this paper, which is still in the archive. Still in the archive only. This is a way to see this type of oscillations or the charge migration, possible ways to do attosecond transient absorption. Here with including the nuclear dynamics. So what one can use is excitation from either from the carbons, or 1s of the two carbons on the triple bond, or from the two oxygens. So these are the ionic states corresponding to the removal of these core electrons. And we derive, of course, transitions between either the carbons KH or the oxygen KH to the valence ionic states. And this is the trace that one would get depending on from where one excites. These are already pulses exist in, let's say, the carbon edge. The oxygen is still barely covered, but this is already coming. And what we did here is, of course, a full averaging over all possible orientations. If we orient, then we can, of course, also pinpoint where the initial hole is created and what is exactly the motion between the two. Now, in the last few minutes, I will just briefly present something that I promised from the beginning, to see what and how one can do this regime where we have many electronic states, and we have some sort of like spaghetti of curves here, which are, of course, many conical intersections. So this is something that we did in naphthalene because of the nice experiments that Frank Lepin performed in Lyon. So these are time-resolved photoelectron spectroscopy experiments. In short, what they do is they ionize the system by short XUV pulse with the spectrum that is shown here. This is the ionization spectrum computed by us, ionization spectrum of naphthalene. And then they come with a weak infrared pulse, which can further ionize the system. This is the double ionization threshold of the naphthalene here. So the weak infrared pulse can further ionize the system. And these are the electrons which they collect and then see how they evolve depending on the delay between the pump and the probe. So what they see is that actually going closer or ionizing closer to the double ionization threshold, actually this relaxation of the population, so the system can relax and going down energetically becomes slower and slower. So this is a bit massaged data that I showed you. It corresponds to mainly ionization of 3 orbitals. So these are groups of states that one forms by ionizing these orbitals. This is a zoom of the spectrum. This is what we get here. These are the orbitals. And in principle, we see that the ionization, let's say, from these groups of states relaxes slower than the ionization of these groups of states. So when we did this dynamic, so we did a Bronycoupling Hamiltonian, we include 23 states and 25 modes of the system. And when we did the propagation, we were a bit surprised that what we got is that if we look in the population of the main states here, in these groups of states, we see an extremely fast relaxation or depopulation of the states, much faster than what is observed experimentally. And not only this, they are in a completely different order. So what we see is, let's say that these states depopulates or relaxes much faster than the green state. Yeah? So this is something that struck us at the beginning, and then we realized it's the coupling here between the non-adiabatic coupling between these very dense states is actually such that it's already meaningless to think about individual electronic states and transfer of population between individual electronic states. So one needs to think about like bands. So these are bands of states, so they're so dense that one form like a band in a solid. And if we look at the population or population transfer in a group of states, which more or less corresponds to what are the first, the resolution in the experiment, and second, the way one can extract this depopulation or relaxation timescale, we get something which is certainly, it's not exactly on top of the experiment, but at least gives everything into right order. So what we see is that indeed going up in energy or closer to the double ionization threshold, these states start to relax slower than states which are lying below. And it can be, so it's quite different from, let's say, the low energy regime where we have few states and typically a few conical intersections. I'm finishing, yeah? I see that you're already nervous. This is the last slide that I will show. So here going in the low energy regime, going up in energy, the states indeed starts to relax faster. So this is the typical situation that we get. And in the high energy or close to already double ionization threshold, we start forming these correlation bands. And in a sense, the wave packets have to go through so many conical intersections in their relaxation down that in a sense they got stuck into the correlation band. So correlation band is not something that we discovered. There's a long history in how they are formed and what they do. What we recently did is to actually show that this is not specific for naphthalene or, yeah, so this is an extremely important way of relaxation in many electron systems. So this is what we recently published. Okay, I will briefly just say a few words in conclusion. So we can do fully quantum coupled electron nuclear dynamics following ionization. Yeah, this can be done with a combination of what we do, of course, is ADC or Green's function, Vibronic coupling, and STDH. One can do both inner and outer valence. With the inner valence, as I said, it's one needs to consider the correlation bands. Long-lived coherents are not completely excluded. So the question, the system not always decohere extremely fast, and the dynamics in the correlation band can be extremely interesting and important. And I will leave the acknowledgements. Yeah, of course, the people in yellow are more important for the work than the others, but yeah, and some financial support. And thank you for your attention.
Thank you, Alex. Thank you. Yeah, indeed. Starting to get a bit nervous with the timing, but it's okay.
I realized that I was a bit modest when I asked only for 30 minutes. Then, of course, they are never enough. I said.
Yeah. Trouble was, I was finding it interesting, so I didn't want to stop you. Yeah. So, does anyone have any questions for Alex? Fernando.
Very nice talk, Alex. I would like to know your opinion about the following. As you know, well, first, doing full quantum mechanical both for electrons and nuclei is absolutely the right way to do it. Now, but as you know, in many experiments, what they measure is ions. So they detect ions that come after fragmentation of the molecule when you ionize it. And from the yields they measure for these ions, they try to get information about the early electron dynamics. So I was wondering if with the approach, the MCTDH approach you are using, it would be realistic to describe the nuclear dynamics until, you know, the dissociation of the cation is produced, and how realistic this would be.
Yes, in principle, it is, of course, MCTDH can deal with such kind of problems. Here the problematic part is, of course, the Vibronic coupling, Hamiltonian, or how you describe the potential. So if you do a normal diabatization of your states, because I think the diabatization in this case is important, then you can, of course, do also fragmentation. So you will have, let's say, channel, which will lead you to a fragmentation. MCTDH allows you to put complex absorbing potential, so you can get also fragments and so on. So this won't be a problem. The problematic part here will be the diabatization of the potential energy surfaces that one needs to do. In principle, in such, if we are talking about larger molecules, what we call large, of course, molecules, then doing full dynamics is relatively complicated, of course. So in this case, one should probably go to some reduced dimensionality, at least capturing the few, let's say, the dissociation channel we are interested in, plus a few, let's say, degrees of freedom, which will be important for the dynamics, and then do full potential surfaces, not like us now cuts within vibrational modes. This, of course, is possible to describe, let's say, the dephasing due to the nuclear dynamics, but of course not if we want to do dissociation, as you said. But in principle, it's possible. One can go there are methods for doing diabatization and do full dynamics on potential surfaces.
Okay, thank you.
Sonia?
Yes, you mentioned ADC. Can you clarify which level of ADC you use?
Yeah, it's ADC 3 what we do, yeah.
Okay,
thank
you.
This, we take into account all 2-hole 1 particle configuration. So everything in the 2-hole 1 particle is covered.
Thank you.
You're welcome.
Is your question very quick, Gilbert?
Yes, it is. So I would want to ask a question about the numerical effort or the computational effort that you had, for instance, with naphthalene. So when you did this 25 normal modes and I think also 23 states, yeah.
Yeah. To tell you the truth, it's not much. So it was more effort was to, let's say, to construct the potential energy surfaces or to run the ADC calculations. This was more effort than doing the propagation afterwards. The many modes, these are cuts, yeah. So these are not full potential. So we don't need a huge amount of space in order to store the also. The wave function. So it is something that I mean, it's not, let's say, weeks of calculation. This is what I mean. The preparation and the constructing of the Vibronic coupling Hamiltonian takes, of course, time. But then the propagation, for example, by the MCTDH is relatively fast. One can do within hours.
Okay, yeah, thank you.
You're welcome.
Okay, so thank you, Alex. And we'd better move on. So our next speaker is Katalin Kovacs.
Okay, thank you very much. Now I share the screen. Is it okay? Can you hear me?
can hear you fine, yes.
Okay, then also you see me now, yes, isn't it? The title of my talk is Macroscopic Modeling of Attosecond Pulse Generation. And I would like to say that our work situates somewhere between Working Group 1 and Working Group 2, in the sense that we try to support experimental groups by modeling and simulation, as I will show during the presentation. First, I give a short reminder about high harmonic generation. Then I give a motivation why macroscopic modeling is necessary. The three-dimensional non-adiabatic model, which I will present, follows the natural sequences of the high harmonic generation. So therefore, I will present the problems related to the propagation of ultrashort pulses, the changes, the temporal and the spatial changes of the medium's effective refractive index. I will present briefly the elemental laser atom interaction and a little bit about the cases when multiple ionization takes place due to very strong, very intense laser pulses. And I also present a case study in this sense. Then we also present the way how we calculate the macroscopic buildup of attosecond pulses with special attention to the time-dependent phase matching analysis. And finally, in order to highlight how important these macroscopic propagation effects are, I will present two case studies, two representative cases based on experiments. High harmonic generation in gas medium takes place like this. An intense femtosecond laser pulse is focused into a gas jet or a static cell. Here, the elementary interaction between the laser and the atom takes place. Then the generated XUV high harmonics propagate first in the same medium together with the driver. Then the XUVs can be refocused or dispersed depending on the experimental conditions. And then finally, hopefully we obtain the measured high harmonic power spectrum. Now at the basic level, at the atomic level, we know very well the three-step model. First, the strong laser pulse distorts the atomic Coulomb potential, and one electron can tunnel ionize. And here I would like to say to keep in mind that exactly due to this case, the basis of this phenomenon is ionization. So we must take into account always in the modeling the ground state depletion. Then the free electron is accelerated, and in the next half cycle, it might come back and recombine and emit the energetic high harmonic photon. Now, due to the fact that this process takes place twice during one optical cycle, the typical high harmonic spectrum in the spectral representation is the odd order harmonics of the fundamental pulse, and temporally these are attosecond bursts, attosecond pulses, a train of attosecond pulses separated by half of the laser period. Now, why is it important to take into account the macroscopic effects during modeling? Because the driver always suffers serious distortions during propagation, just as you see here, for example, this input laser pulse, the black one, after short propagation in the gas medium, accumulates a cell phase modulation and both a decrease in the intensity. And then these two pulses basically result or generate completely different dipole spectra. The black spectrum corresponds to the dipole spectrum of the initial pulse, and the red one has a lower cutoff due to the decrease in the intensity. And also what you cannot see, but if we zoom in, we can see that also the individual harmonics, the red ones, are blue shifted due to the cell phase modulation of the fundamental pulse. So we always have to include propagation effects, and this is not science fiction. This is almost exactly the beamline, one of the beamlines at Eli Alps. Therefore, I motivate that the purpose of the modeling is to faithfully reproduce as faithfully as possible the experimental conditions. And for this purpose, our model uses as input parameters almost always experimentally measurable quantities like pulse energy, pulse duration, central wavelength, waste. We try to account as exactly as possible for the focusing, for the clipping of the fundamental beam, for the geometry of the whole system, to include the gas properties, what kind of gas, what's a pressure, if there is a pressure distribution, and somehow to make a trade-off between accuracy and computational time, but really never, we always favor accuracy. That's what I wanted to say. The structure of this model follows the physical phenomena. We first construct the input case, the input pulse, initial pulse based on experimental data or information. Then we solve the propagation of the fundamental pulse, solve the single dipole response in the laser atom interaction, and then propagate the harmonics and try to see the conditions for a good build-up, a coherent build-up of the final high harmonic radiation. These models are based on the seminal paper of Priori, but further developed to account for or to capture as many experimental conditions as possible. So then first the propagation of the ultrashort laser pulses. This is not a first big part of the modeling and not trivial at all. First we construct the initial pulse. I will show it immediately also with formulae. These can be Gaussian beams or truncated or Bessel beam if it comes from a compressor. Then we solve the wave equation in we write the wave equation in time domain, but then we solve it in frequency domain and in cylindrical coordinates, because we assume a cylindrical symmetry of the for the whole system, and solve the equation self-consistently. But what I want to highlight here is that the non-adiabacity of the model comes from the fact that in each spatial step, the modified, the distorted electric field is calculated, and so it is also the effective refractive index updated during propagation. So how we construct the initial field? Now here I just show a Gaussian pulse, but it can be not necessarily Gaussian. It has a spatial envelope, it has a temporal envelope, and in the phase part it accounts for the spatial phase, and it accounts also for the CEPs, for the chirp, whatever is needed. This input pulse can be everything, including data coming from spectral intensity and phase measurements, so as real as possible. This is the propagation equation. We know it very well, but what is interesting is that the source term itself is the unknown field. So this is an explicit dependence on the unknown fundamental electric field, but also the effective refractive index accounts for many things, accounts for the dispersion on the neutrals, the linear dispersion, accounts for the Kerr effect, the nonlinear Kerr effect, which is again an implicit dependence on the unknown field, and most importantly accounts for the plasma term through the free electron density, which again depends implicitly on the unknown, on the shape of the unknown field through the free electron density in the medium. Finally, after all the transformations, this is the analytical form of the equation we solve using a self-consistent iterative method, which is one big part of modeling. And again, in each step, the field and the refractive index are updated according to the instantaneous situation. Let me a little bit demonstrate or show which term in the effective refractive index is more important. If we here we see the evolution of the peak intensity of a pulse as it propagates through a medium. This is these are I don't insist on the actual parameters, but this is a very usual set of parameters, a very everyday pulse nowadays. And if we switch on and off successively different terms in the refractive index, we can see that if we turn off, for example, the plasma term, then the evolution of the peak intensity of the pulse barely changes, is almost like the vacuum case. So we can conclude that in most cases, the plasma term is by far most important contribution. The laser atom interaction at dipole level uses in our model uses the strong field approximation. We make sure to be within this approximation. The nonlinear dipole response is calculated with the Levenshtein integral, which we know the physical meaning is that here is the ionization transition matrix element. This is the phase accumulated by the electron during its excursion. We calculate it using saddle point approximation, the matrix element for the recombination. But always we take into account the ionization for the macroscopic nonlinear response, which is a non-trivial task. And I will not very much insist on this because we heard nice presentations during this conference treating this non-trivial problem of ionization. And we also, as a consequence of the ionization, we always take into account the ground state depletion when we calculate the macroscopic nonlinear response of the atom. Just a few words about the used ionization models. We use basically the ADK model, but depending on the atomic species, depending on the intensity regime, we usually apply corrections based on calculations and experimental data. As I just indicated, several papers we base ourselves on, but depending on the problem itself, we can adjust the ionization model. What is important here is that always we calculate the ionization rates for an instantaneous electric field. As lasers are stronger and stronger, the multiple ionization of atoms becomes a real problem and has to be solved. Now we implemented a successive multiple ionization model based on this paper of Gonzalez, and we solve a set of rate equations for the sequential, the successive ionization and the depletion of the population of different ionic states. And finally, we can obtain the total free electron density, which is a very important quantity, as you saw in earlier slides for the nonlinear response. Let me show a case study for this multiple ionization case. We constructed a pulse which reaches around 10 to the 16 watt per square centimeter intensity at the cell entrance, and it can cause, and it enters into an argon medium, and it can cause ionization of up to argon 6+. And here I show how during the rising part of the laser pulse, this is its envelope, different species of different charges born, to say like this, so their population increases and their population decreases and depletes due to further ionization, again up to argon 6+. And this is how the laser pulse, its temporal shape of the input of the generating laser pulse distorts and modifies during propagation. And we can also see here bigger steps in ionization. This is these are the time moments during a pulse evolution when the new species, the higher charge ionic species starts to dominate. Let us look a little bit in space domain, in spatial domain. This is how the spatial map of the ionization degree looks like just after the pulse has gone. You can see these regions in the spatial domain where different charges of ionic species dominate. And this causes a very serious distortion of the laser pulse. This is how its peak intensity evolves. And let me show in these different points during propagation, I show only on-axis situations of the laser pulse, how seriously it is distorted. This is only the envelope. This is not the carrier wave, yet the envelope distorts to such a degree, so we cannot expect some nice high harmonic spectrum. Only at single dipole level we can see along the rising edge of the pulse how different ionic species generate their own dipoles. This bear in mind that these are of the higher, the dipoles generated with the higher charges are multiplied because otherwise they are not visible. But what did I do? But the combined dipole spectrum of all the ionic species finally leads to a so-called multi-plateau high harmonic spectrum. This is an interesting case, and these pulses again are at hand already. The macroscopic buildup of these elemental dipole emissions consists the third big part of our modeling. The emitted dipoles propagate in the same medium together with the driving pulse. Therefore, a similar kind of wave equation has to be solved for the harmonic field. The easier thing is that the source term here is the nonlinear dipole, which is already calculated. It is known, so there is no need for a self-consistent iterative method to solve it. After we solve this equation for each spectral component of the harmonic field, the medium is over. The XUVs exit from the interaction medium, and then they are transported to the detection. We call it to the far field, and we use the ABCD ray matrix formalism and solve the Hankel integral. Here we can include refocusing, whatever is the real experimental configuration for this case. A very important part is the time-dependent phase matching analysis of this model. We know from the seminal paper of Philippe Bacou and co-workers that they gave static model for the phase matching, and the condition for a perfect phase matching is when the wave vector of the qth order harmonic is exactly equal to the wave vector of the polarization. Now, the time-dependent generalization of this static model takes into account the modifications of the fundamental electric field, and we use here a spectrally averaged phase and intensity for the laser field, and both of these are obtained from the propagated solution of the wave equation, which was the first point of this modeling. The degree of phase matching is quantified by the phase mismatch or its inverse quantity, the coherence length. And as a practical guide, we say that there is good phase matching in those cases when the coherence length is comparable to the generation medium's length. This is a paper where many papers, but I just highlighted one where we studied in detail these phase matching effects. Let me show two cases, very representative cases, two very different cases, but both of them are real cases. The first one I named case long because this is the long focusing beamline, one beamline very similar to the silos at Eli Alps. This uses an 800 nanometer driver, and here the goal is to optimize the XUV efficiency around certain energy we picked up for 40 electron volts. The second case, we call it lighthouse case. This is a compact beamline with tight focusing, uses mid-infrared driving pulse, and the goal is to demonstrate the attosecond lighthouse effect. Here I just summarize their parameters just to show at a glance that they are totally different. For this long case, we did a multi-parameter scan, and I just pick up one from the many parameter combinations. Please observe here the strong cell phase modulation of the input laser pulse and its intensity clamping. And let's, these are the graphs I already showed at the motivation point. How different are already the dipole spectra of these let's say two pulses, or the non-modified and the modified pulses at the beginning and at the end of the propagation. And the macroscopic high harmonic spectra are not even remembering of the dipole spectra, but what we can see is that at a certain propagation distance, which is 4 centimeters in this particular case, somehow emissions around 40 electron volts, which is harmonic 25, they somehow find good phase matching conditions, and here the signal is optimized. Let's see how this happens both in time and in space. Let's see the spatial evolution of the driver pulse. This is the same quantity, the peak intensity of the driver in two representations, because I want then you to compare the shape of the driving pulse with the spatial build-up of of this harmonic 25, and please observe here where the gradient of the field has a certain value, there this harmonic finds good phase matching conditions. Let's see whether the coherence length calculations confirm this. And let's bear in mind that this phase matching calculation, this coherence length calculation, is a completely independent way of verifying what happens in the macroscopic model. Let's see what happens in time. Look at this pulse shape and observe that exactly in those few optical cycles, few optical half cycles, the best emissions occur exactly when the ionization degree and consequently the refractive index of the medium changes most rapidly. And exactly in these optical cycles with gray, we have in the near field the best, the strongest high harmonic emission. These are time and radial representation. And if these emissions are collimated and are with low divergence, they will sum up around the optical axis in the far field and give a strong high harmonic signal exactly on axis. I want to stress that all these information are really unavailable experimentally, so our modeling can be of real help.
2 minutes, please, Kathleen.
2 minutes. Okay, then 1 minute for the lighthouse case. This is another configuration. We used here mid-infrared pulses because these are much more sensitive to the changes in the refractive index of the medium. And the main goal here is at the lighthouse effect, if you are not familiar with it, is to radially separate successive attosecond emissions so that there is no need for further spectral filtering in order to obtain single attosecond pulse, but these temporally successive emissions will radially separate and naturally give rise to single attosecond pulses. Let's see, again, please observe the very strong cell phase modulation during propagation. This is only 1 millimeter medium. So it's not centimeters, not meters, 1 millimeter argon medium, but being it mid-infrared pulse, it is much more sensitive to these modifications of the refractive index. And the spatial map of the laser peak intensity is very nice because after a short distance of propagation, it drops and it enters a so-called self-guiding regime, which is macroscopically very advantageous for the build-up of certain harmonics, which here we can see it's above 100 electron volts, which can be a real treasure for further applications. How this lighthouse effect occurs, the wavefront of the basic mid-IR during propagation, the wavefront is distorted, it rotates, and all these waveform rotations or pass front rotations are inherited, are transmitted to the high harmonic dipoles, and in successive half optical cycles, these high harmonic emissions are emitted with increasing divergence, and if they have different divergence, then in the far field they separate radially. These are several sections of this radial separation. This is not perfect. Of course, it is not perfect radial separation, but we wanted to stress that we did not use any external dispersive element like a glass wedge, which is usually used, but this is the way how the natural macroscopic propagation effects facilitate this attosecond lighthouse effect. In conclusion, we presented these three-dimensional non-adiabatic model where macroscopic propagation effects are taken into account. The reshaping of the fundamental pulse is taken into account, and then we see how its reshaping affects the single dipole and, of course, the macroscopic buildup of harmonic radiation. And I presented 3 case studies, one for the multiple ionization, one for the optimization of a long focusing beamline, and one case to demonstrate the attosecond lighthouse effect. Thank you for your attention.
Yeah, thank you, Kathleen. That's yeah, it's very interesting to see all the details of actually how the laser interacts with a molecule or atom that, of course, those of us who simulate molecular properties ignore totally. So we have time, I think, just for one very quick question. If someone has a very quick question before we sort of move on. Because if not, given the time, we will come on to our last talk of this session. So just to finish off, we have Jakub Bender, who I believe is in Prague. He may have said at the beginning.
All right. So
Jakub, over to you.
Okay. So in this last talk, I will conclude the section with another presentation about the Armatrix theory, which was reviewed by Jimena at the beginning of this session. The subtitle of this talk is Time-Independent Armatrix Multi-Photon Ionization Formalism, which actually might be a little bit more descriptive than the main title. In other words, I will be talking about perturbative calculations in the Armatrix method. I will build on what Jimena already said, but I will generalize the one-photon results to higher orders. For the calculations or implementation of this method, we used the UKRML Plus program suite, which allows us to take advantage of the full generality of the possible targets that can be used, atoms, molecules, bigger things, as well as the methods of their quantum chemical descriptions. So, as I said, I will not venture beyond the domain of the weak fields, and I will begin the first section will be illustration of the method on a few motivating results containing mainly cross sections on atoms and molecules. In the second part, I will touch a related topic, a multi-photon process called Rebit, and I will explain how the method actually works in the last part as much as the time allows. So first of all, I start with very simple results. Here we see both below and above threshold ionization cross sections for 2-photon ionization of atoms, the hydrogen and the helium atom, calculated by the Armatrix, the newly developed Armatrix approach, and compared to results from other researchers, other calculations. We see a very, very nice agreement, except perhaps the higher energies in the case of helium, where this deviation from other calculations is not really a sign of a breakdown of the method. Rather, it's a limitation of this particular calculation, which used a specific Gaussian basis set for characterization of the ionic states of the helium. And this particular basis set is not sufficiently diffuse to describe highly excited states of helium, which then manifests as deficiency in description of the core excited resonances. However, as I said, with the UKRML Plus package, we are not limited to atoms and can go straight to molecules in the same way. So here, another motivating example, 1, 2, 3, and 4-photon ionization cross-section for hydrogen in a static exchange or single channel approximation, and for a specific polarization parallel to the internuclear axis. Equally well as the static exchange model, we can go to higher models thanks to the flexibility of the configuration description in UKML+. And so here I show the photoionization cross sections for the 2-photon ionization of H2, but in full CI approach. In the leftmost figure, in the leftmost part of that figure, you may recognize the curve that you have seen already in presentation of Jimena. However, here the cross sections are extended to much larger range of energies above the ionization threshold. We compare our results here again to calculations by other researchers. However, this time there are actually no results, or we have found none results for the above threshold ionization, which leads us to comforting feeling that we are the first to actually calculate these. So that would be the motivation. Now, second part focused on Rabbit experiment. So the Rabbit process is 1+1, I would say, absorption of 2 photons, where the first one has large energy, it's an ultraviolet photon, and it ionizes the molecule, and the photoelectron, which is released from the molecule, then absorbs or emits another photon, a low energy one, infrared. So if there are multiple XUV wavelengths, this experiment can give rise to interference phenomena for 2 different pathways, which are shown here in the figure. And this then manifests in as beating in sidebands observable in the photoionization yield that depends on the relative phases of the fields. As it is introduced here, this is a 2-photon process. So, of course, for correct characterization of this process, a 2-photon or second-order theory is necessary. So the objective of the Rabbit experiment is the measurement of the so-called sideband time delay, for which a formula is here on this slide. In absence of accurate 2-photon or second-order theory, or also for purpose of analysis, it's customary to split this sideband time delay into so-called molecular delay and measurement delay. There are different names also for these quantities. The molecular delay can be calculated, for example, by here formula from Baikusheva and Werner, 2017, where the molecular delay is expressed in terms of the quantity B, which is nothing less than some combination of the partial wave 1-photon transition amplitudes and, of course, some angular momentum algebra. It's interesting that one can find in this algebra, in this formula, resolution of identity, which can be summed to provide actually a result that this B is directly proportional to the 1-photon amplitude, 1-photon transition dipole element, together with the observation that the molecular time delay is actually nothing else than the discrete approximation of the energy derivative. It can lead us to conclusion that this molecular time delay introduced in Baikusheva and Werner is actually the same quantity as what is referred to the 1-photon or Wigner delay defined by means of the first-order amplitude. Besides this molecular delay, we talk also about the measurement delay, for which there are different formulas, because being an approximation, it can have different forms. So, for example, here, again, Baikusheva and Werner provide this fairly complex expression, which is target independent and only depends on the momenta of the electron before and after absorption of the second photon. So, yeah, as I said, different authors provide different formulas. So the advantage of having access to an accurate second-order theory, as we do, as is the one that I am showing to you here, is that we don't need to split this sideband time delay into these 2 contributions. and we can calculate or simulate the process directly by means of the 2-photon amplitudes. And this is, for example, what we have done for the hydrogen molecule. So here in this plot, you see several things. First of all, the black curve, the dashed one, is a calculation of the sideband time delay for specific polarization and orientation of emission in the time-dependent code that Jimena introduced as well at the beginning of this session. And we show here also the result of the newly developed second-order Armatrix time-independent theory in blue. And we see that apart from some divergence in the high energy region, these two converge very nicely together in the limit of low energies. However, this can be said for the approximations, for the splittings. We calculated with the same model, static exchange model, we calculated the first order delays, which are the purple curve, and attempted to add all available measurement corrections to this first order delay. And even though eventually at high energies, these converge very well to the second order results, at low energies, they just can't compete with the full second order theory. When we move to a more complex model, the full CI model in hydrogen, the picture does not change much, except perhaps it becomes a little bit messy due to the presence of the resonances. But we see that again, the time-dependent calculation, the black curve, and the time-independent second order calculation are very, very close to each other, in contrast to any approximation, any asymptotic approximation that uses the splitting of the sideband time delay. These time delay energy dependencies have very often quite interesting properties or features. Here we see a very wide hill-like structure at around 40 electron volts of the photoelectron kinetic energy. This feature is caused by interference of partial waves or partial contributions to the total transition dipole element. The P wave and F wave interfere at around 40 electron volts, giving rise to rapid changes in the total phase. And this is actually related to the fact that the P wave dramatically decays with a minimum at around 70 electron volts. And that is related to a destructive multi-center interference for photoionization of a diatomic molecule, as discussed in this reference. We performed a similar calculation also for a different molecule, for the nitrogen molecule. This time the figure is a little bit clear. There is just the first order, second order, and the time-dependent calculation. And we then see that the black calculation, the time-dependent one from RMT, agrees very nicely, follows very closely the second order calculation from the time-independent code. Apart from a similar interference structure at 50 electron volts, we also see a new feature here at 20 electron volts of the photoelectron kinetic energy. And this one is actually related to the presence of a shape resonance in the F wave, or in the L equals to 3 contribution to the total dipole element. So these were the illustrations of the new method. And in this third part, I will try to explain how the method works. When dealing with multi-photon amplitudes, we are calculating matrix elements like this. So it's a matrix element of a chain of dipole operators and Green's functions of increasing energy. And as we have heard in the talk by Andrzej Michalic yesterday, a very nice talk, on a similar topic. These matrix elements can be calculated by means of a solution of sequence of Schrodinger equations, driven ones, and this is followed by evaluation of a single dipole element between the so-called final or the last intermediate state and the final photoionization time-independent scattering state. So all these Schrodinger equations are more or less the same. On the right-hand side, there is either the initial state and the dipole operator, or the previous intermediate state, and on the left-hand side, there is the unknown intermediate state of one by one higher order. The main task of this multi-photon Armatrix method is then to calculate or solve this equation at each iteration, at each photon absorption order. And this is done in the following way. So as shown by Jimena, we use a specific channel expansion in the out region, because here we assume that only one electron can be present, the photoelectron, and hence we can combine the total wave function from the channels where the radial function of the photoelectron multiplies some channel functions, which are a combination of the ionic state function of the residual ion states and the angular or spin angular part of the photoelectron wave function. In the inner region, on the contrary, we expand the wave function, all of them, the known and the unknown wave function, in terms of so-called inner region or Armatrix eigenstates. These eigenstates are properly antisymmetric and multi-electron states, which include as many correlation as we want and as we put in by choice of a correct or useful quantum chemical model. And they are eigenstates of the total many electron Hamiltonian augmented by a so-called block operator, which makes the total operator Hermitian in the inner region. One important part about this method is that in the outer region, so beyond the radius of the inner region, we assume that we can consider only the central Coulomb potential. So at this moment, we disregard any possible dipole or multiple potentials, which is mostly fine because the Coulomb potential is typically much stronger and dominates the interaction. The method proceeds then by splitting the right-hand side. The right-hand side is expressed as a sum of the source that is constrained to the inner region and its complement that is constrained to the outer region. So it's really spatially separated by the Armatrix region. And having the right-hand side as a combination of two terms, we also expect that the solution at, for example, the boundary between the regions and also for higher AD will be a combination of solutions generated by these two separate sources. To be more specific, in the outer region, where there is, as I said, we use the channel expansion and there is no dipole or higher multiple coupling, this multi-electron Schrodinger equation decouples into a set of independent one-electron wave functions. And because the only potential in this outer region is the Coulomb potential, we can actually solve this equation, these one-electron equations, by means of the Coulomb-Green's function, as written here at the bottom of the slide. This integral can be actually calculated analytically, and I will come to that in a moment. Regarding the second part, the inner part of the right-hand side, or the source term, we observe that in the outer region, it will manifest only as a source for purely outgoing waves that leave the inner region and propagate through the outer region. So we can say that the part of the solution in the outer region, which is generated by the inner region part of the right-hand side in each channel, so this is a projection into channel, is proportional to an outgoing Coulomb wave in case of open channel, or to the exponential decaying Whittaker function for closed channels. As I said before, these two solutions can be combined. So together, we expect that in the outer region, the unknown wave function can be expressed by means of the known intermediate state from the previous absorption order by these formulas for open and closed channels. And the only unknown element here is the coefficient of proportionality, this AP, which needs to be found. On the so that solution is valid in the full outer region, and this means that it's also valid on the boundary of between the inner and outer region. And as such, and thanks to the continuity of the unknown solution, or the assumed continuity, we can replace it at the boundary of the inner region by the inner solution, because they are equal there. So we get at the Armatrix boundary such conditions for projections of the inner solution into the one electron channels, that they are proportional to an outgoing Coulomb wave and augmented by some analytically calculable integral containing a single channel Green's function. This equation can be reorganized by transferring the integral term from right-hand side to left-hand side. And we see that this expression on the left-hand side needs to be proportional via some unknown coefficient to the outgoing wave, or exponentially decreasing one. So the right-hand side is unknown function, but the right-hand side has a known logarithmic derivative, because when we calculate the logarithmic derivative of the right-hand side, the coefficient will cancel, of course. And it turns out that by some miracle, requiring that the logarithmic derivative of this circled term is equal to this known logarithmic derivative of some asymptotic functions is quite enough to solve for the inner region. I will not show the full exposition, just this is these are the equations when put all together. So we see here at the top of the boxed region that this is the equation for the expansion coefficients of the unknown solution in the inner region in terms of the Armatrix eigenstates. It features various things like eigenstates of the inner region eigenstates, a modified block operator, which includes the required logarithmic derivative. And on the right-hand side, there is the inner region part of the right-hand side projected into a specific eigenstate. I see that Graham turned his camera on. I think I still have quite some time, no? Okay. Having the inner region expansion coefficients, we can easily calculate the outer region wave function as a projection on the channels. I mentioned that the method requires calculation of some analytic integrals. These are actually quite intimidating ones, because they are infinite integrals of widely oscillating functions, which can even diverge. However, these integrals can be regularized using an exponential damping factor, and it turns out that in the limit where this exponentially damping factor disappears, the integrals stay finite and well-defined. To calculate these integrals, we use asymptotic expansion for the Coulomb-Hankel functions, which looks like this, which transform the integrals into integrals containing just exponentials and some relatively slowly varying functions of the coordinate. And these can be calculated by means of the method of Aymar and Kaunz from 30 years ago, which amounts to calculating a few terms of the integration by parts. And this converges very, very fast, and just 2 or 3 terms of this are actually required. For higher transitions than two photon ones, we need much more complicated integrals, multidimensional integrals of, again, Coulomb-Hankel functions and Coulomb-Green's functions. These can be, again, expressed using the asymptotic development of the Coulomb wave functions in terms of exponentials. And it turns out that these integrals can be calculated in a recursive way, because we have seen on the previous slide that the one-dimensional integral of the exponential times something is eventually exponential times something again, which can be merged with the next integrand and calculated this way in terms. There are some limitations to this method. I mentioned, well, analytical integration and asymptotic expansions. These are quite fine if the Armatrix radius is sufficiently large, because then all these asymptotic formulas converge very well. If we are too close to the molecule, these formulas do not converge, but we can help it very simply. We can just calculate those integrals numerically in some finite region between 2 different radii and use the analytic integration onward. And this solves the problem. So here just a very, very simple example for 2-photon ionization of hydrogen calculated with Armatrix radius 15. That's the blue curve. But once we extend the inner region, or as if shorten the outer region by means of the numerical integration to 150, we get results that are indistinguishable from results obtained with inner region size 150. There are some other limitations. Of course, I mentioned that we are dealing with low intensities only. We are in the perturbation theory. We use dipole approximation, and as you have seen, length gauge. And this all is valid for fixed nuclei, but nothing prevents us from doing, say, vibrational averaging. To sum up, so we derived a new method based on the Armatrix approach that is applicable to both atoms and molecules. It is time dependent, and it can calculate more or less arbitrary multi-photon ionization amplitudes. The fact that it's time independent, of course, makes it computationally efficient, because otherwise these quantities were often calculated using time dependent methods, which take quite some time. I mean, computational one. Right, so it's based on a separation of the multi-photon matrix element into a sequence of Schrodinger equations. The proper boundary condition is embedded at the boundary of the inner region by means of a modified block operator. And we also provide a recursive algorithm that evaluates multidimensional free integrals needed for treatment of the outer region to complement the wave functions. We applied this method to multi-photon cross-section calculation for hydrogen atom and molecule and for helium atom. And I've also shown some 2-photon transitions in the rabbit experiment for hydrogen and nitrogen. And with that, I thank you very much for your attention and sharing.
Thank you very much, Jakob. Okay, so it's time for a couple of questions before we stop. So how should you choose the the Armatrix radius? Because they sort of seem to say that obviously you should get the same result sort of whatever you choose it, but what guides you in how close in or where you put it?
Well, I think that the best answer is that we do ideally some radius convergence test. So okay. we try several radii and see from what radius the results are unaffected. Okay. Normally it's enough if the inner region actually contains all electron density, but sometimes it's useful to extend it.
Yeah, and you don't want to go too far out because then you need a really large, long outer part. And so, yes. Okay, so it's just that. Yeah, it's a bit of trial and error.
Yes.
Hans Jakob? Yes, thank you for the nice talk, Jakob. Very nice presentation, great results. I have a comment and a question. So first, the comment is indeed, so the finite difference approximation is not a small approximation, in particular when you have resonances, as you nicely showed also in H2, for example. And in our paper that you cited with Denitsa, we showed this quite explicitly because we showed that there are very big differences in the 2-photon and 1-photon delays. In the case of N2O that we studied experimentally back in 2016, where we showed that the rabbit time delays contain information about the lifetime of shape resonances. And we showed that in that case, in that specific case, although you have a very broad shape resonance, there is a big difference between the 2-photon and 1-photon delays, even after taking into account the CC delay. And that comes because of a failure of this finite difference approximation. And that will be much more significant when you have narrow resonances, of course, because then you have rapid variations and the finite difference approximation becomes almost meaningless. And the other case where it seems to me there is a very big difference between 1-photon and 2-photon delays is in the angular result of time delays. Because as you may know, in the case of helium, there is a strong angle dependence to the 2-photon time delays, also those measured by rabbit. And there is, of course, no time delay at all in the Wigner delay itself because of the spherical symmetry of 1s. And this is even more significant in the case of molecules. So in molecular frame time delays, where there is essentially no direct correspondence between 1-photon and 2-photon at the simple level. And so my question after this long comment is, have you done calculations in the molecular frame? Is this possible with your code?
Well, yes, we can do that. We have done only calculations that you have seen, so we have nothing hidden yet. But we plan to do more, and we definitely will revisit these rabbit time delays again. So,
okay, then I look forward to seeing that and hearing from you.
Thank you.
Okay, right, seeing as we are running a few minutes late, if there are no other questions, I suggest you leave all of your questions and go to the Meet the Speaker rooms to ask whatever you would like. And otherwise, just leaves me to thank the speakers from this morning's session. So Jimena, Alex, Katalin, and Jakob for your great presentations. And I think everyone is due back, well, it's now 50 minutes time at 1:40 for some more Armatrix calculations.